Good day, people of Sensat. This is the start of a long set of series. I thought I'll share some information with you guys, and it's mainly about. There's a lot of information that we can share. We normally do the WTFs in the office, but some of the knowledge gets stayed within either those sessions or PowerPoint presentations. So I thought I'll start creating these small little video clips. Small, we'll see how short this video clip goes. This is just a sort of a starter. But I'll start with two series. So I'll separate them out into series of topics. First topic is all around projection and coordinate referencing systems. There's a lot of discussion going around nowadays, so I think it's quite topical. The second one will be around spatial data and what sort of spatial data they are, and then how we can sort of manipulate them or understand a little bit more about the structure. But today's episode is all about projections. And it belongs to the full series of the world of coordinates that we will talk about. So today we're all going to talk about projections and see how we can actually take that 3D world and then really turn it into the 2D world. Why do we do that anyway? And what sort of issues that we can come across. So this whole world of sort of coordinates and projections all comes down to the fact that what the shape of the Earth really is. Well, take a guess. I'll give you 2 seconds to take a guess what the shape of the Earth might be. Think of an ordinary object that best represents the shape of the Earth. Well, it's a potato. Yeah. So our Earth very much resembles like a potato. And it's very knobbly. It's not regular. It's got weird inundations everywhere. So it's mathematically it's nearly impossible to map the whole potato. There's no single equation that will be able to do that for us. But we do want to make measurements on this knobbly Earth or a potato. Now, this is what we've been told the Earth looks like. Some people think it's flat, but this is what we've been told when we look at our Earth, the blue marble from the space. It looks so simple. It looks just like a nice little regular sort of circular spheroid, but it's not. It gives an impression that it is, but it's not. If it was this simple, then we'll have happy geographers all the way around. There won't be any sort of discussions around which coordinate systems or which not, what projections. They'll all agree on one simple mathematical formula that will pretty much agree to this simple shape. But I'm afraid that's not the case. That is what we have come closest to in defining mathematically what a shape might be, what Earth might look like. Again, as I mentioned, potato. This looks like a potato. So the Earth shape technically is considered to be a geoid. So this is a shape that in geometry didn't exist, so they had to create it. And again, it's an approximation of the knobbliness of the Earth. That's the closest we can come to. This is still not the real shape, but it is the closest approximation to the shape of the Earth. And it's known as a geoid, just like a spheroid or an ellipsoid. This is a 3D version of a geometrical shape called a geoid. And a geoid is nothing more than an estimation of what the Earth's surface might look like if it was covered by water, and then the water surface was only influenced by Earth's gravitational force and the rotation of it alone. That's it. No weather or tides or winds affecting the surface of the water. So you will imagine that the areas where there is a high gravitational force on the Earth, the water will actually start to accumulate, and the water levels must be much higher because of the gravitational pull. And where the gravitational pull is less, it depends mainly on the density of the rocks as well. And where the gravitational pull is less, there will be less water. The water surface will dip down because the water has been taken away towards the high gravitational areas. And that's what you see here. So the red areas, the knobbly bits, are where the high gravitational areas are, and the blue dips are where the less gravity is. So gravity is not constant on Earth as it was made to believe in school lectures. But that's what the Earth shape or approximation of the Earth shape looks like. Well, that's good enough, right? But the problem is, it's still mathematically very difficult to map this potato-like geoid, even though it is an approximation. It is the closest approximation that we can come to the knobbly Earth. But this is not mathematically possible. It's not mathematically possible to, again, map this whole geoid with one equation. Okay? So we really can't find the mathematical solution to this. So if you start off with looking at things, you see that Earth actually is very knobbly. We approximate to be less knobbly in a geoid shape, but it's still quite lumpy. So then the next step is to actually even approximate it more, simplify it more, to be an object that mathematically can be mapped. And that normally is either an ellipsoid or a spheroid. So in this particular image you see here is an ellipse. So imagine that in a 3D shape like an egg. Egg is a slightly distorted shape, but anyway. So this ellipsoid is what we normally work with in all sort of GIS systems or in CAD systems. That's the ellipsoid. That causes a lot of discussion. Okay. But somebody in the past, a very clever guy, suggested that the Earth shape is not a perfect ellipsoid or a sphere. It's an oblate sphere. Can you guess who that might be? A nice looking chap with curly hair. Newton. Newton suggested that our Earth is an oblate sphere. And what's an oblate sphere? It's basically, if you imagine our Earth's poles to be top and the bottom, and the equator in the middle. So oblate is basically the poles are squashed. So they're pressing, so they're flattened. While that pressing happens, the equator bulges out a little bit, just like my tummy. It bulges out a little bit around the equator. So that's what an oblate looks like. Okay, so you see the oblate shape or the oblate spheroid or sphere is sort of compacted from the top, poles are flat, and the equator is bulging out. So that's why we take it as our reference, mathematical reference, and we start to sort of map things around it. So I would like to talk a little bit about maths. Actually, let's not do that. Let's just carry on talking about how easy it is now that we have taken this geoid and sort of approximated to an extremely simple mathematical shape called an ellipsoid or a spheroid. Again, ellipsoid with an eggy shape and spheroid with a round. But they are used either way. Some projections will use ellipsoid, some projections will use spheroid. So it's easy peasy, right? Now we have a regular shape, so it should be easy to map the whole world in one projection. But that's not the case. It's just it becomes impossible. this 3D shape of the Earth, that is, it causes problems when we actually simplify it. So I'll give you an example. So imagine if this red shape that you see out here is an ellipsoid, some sort of ellipsoid that we've actually approximated to. Now, around the edges of the ellipsoid, where it meets the surface of the Earth, bingo, all good. Everything mapped in that area will be perfectly fine. But if you look at the areas where there is a big discrepancy between the surface of the ellipsoid and the surface of the Earth, we're going to get errors. We're going to get errors. So we can't take a simple mathematical shape and try to fit it onto this approximation of a potato, because some parts we will be able to map properly and the other parts we won't be able to. The other parts are going to give errors. So what do? We introduce another ellipsoid. So we said, okay, well, we'll map the top of the Earth in this particular example with the red ellipsoid. And then we'll map the bottom of the Earth with a slightly different ellipsoid. And this is where it all starts. This is where we start deviating away from the shape of the Earth and talking about the approximation and which approximation needs to be used for a particular country. So in this case, for example, one of these ellipsoid could be the NAD83, which is normally used for North America, and the other one could be for WGS84, which generally is used globally. These ellipsoids, these different sort of approximations that move around depending on which area of the world we're trying to map, they call datum. Okay, so that's just a term that is commonly used. You won't come across any client talking about datum, some do, but normally the information about which datum is being used in a coordinate reference system is normally embedded in the metadata. So now when you see the word datum and you see some sort of WGS84 or a NAD83 or GRS associated to it, you know that they're talking about a particular ellipsoid, which is approximation of the geoid, and has been used to map. You still with me? So let's see what sort of errors we can actually get. So earlier on, I mentioned that when you take one ellipsoid and you try to map the whole world with it, it's not going to be able to cover the whole ground appropriately or without any errors. So if you take a particular geoid, let's say a geoid that we've created, and well, yeah, there are many geoids as well, but let's take a geoid that's EGM96, again, a particular geoid approximation. And let's take WGS84 ellipsoid, and then try to sort of match the two together. These are the discrepancies that you're going to see. So the red areas are where we're going to get a plus sort of a difference, and then blue areas are where we're going to get a negative difference. Okay, so yeah, you can see now that if you just use WGS84 reference ellipsoid to map the whole world, only certain parts are going to get mapped appropriately. We are eventually going to produce errors. And then you can see that the errors could be huge as well, hundreds of meters, if you're not careful, if you don't know. So the summary of it all is that mapping the whole globe with one reference is just not possible. Okay, visually it could be okay, but accurate mapping globally in 3D, not so good. So with all that background information, let's come to the part where we talk about projections at last. So this is what this whole episode was about. So what is projection? So it was difficult enough to map the world in 3D, so we thought in the history, as humans, as experts, that let's take that 3D environment, which is too complicated. We're not going to be able to deal with that, and simplify it into the domains. Okay, so let's create a 2D world. And then it was mainly dictated by the fact that the 3D world, people couldn't carry globe around with them for navigation or for mapping purposes. So they needed a reference, and paper was a good reference. Paper was a good material and a platform to actually transfer that information, map the world. So we decided to take that 3D world and bring it to 2D maps. But that required the 3D world to be projected onto a 2D surface. Okay, so 3 dimensions into 2D, 2 dimensions. And this process of taking that 3D world and then flattening them onto a 2D map, or 2D paper, is the process is called projection. And there are many ways of doing that. Okay. So another everyday object that we actually use. Okay, so I have something I made earlier. Actually, this is not the one. This is the one. So something that I made earlier. So this is not a geoid. This is like that ellipsoid. So it's quite regular in shape. Okay, this is in 3D. So what do we do if we want to take that 3D world and put it into a 2D plane? So we start to cut it open. But we've got to do that very, very carefully. To take a 3D. Now, wow. That's my map. So you see that I have managed to take the 3D world and try to flatten it, but it's still extremely difficult to keep it completely flat. So I'm going to have to make some more tears. So let me see if I could tear that bit up. Aha, that's closer. Still quite tedious, but I think that's quite good. You see that now I've taken that 3D world and turned it into a relatively 2D plane. Okay. Wow. So this is a process called projection. In fact, we've done this before at Sensat in 2018 when I first gave the WTF on projections. Obviously, not many of you were there at that time, and these were the results. So I asked many people to peel the orange in different forms, trying to keep the peel intact. And you can now see that even so for 8 people that did this exercise, came up with a completely different way of creating 2D projections from that 3D world. You can see some similarities. So this one and that one and that one and that one are peeled in a pretty similar way. But then the other ones, and especially the one right on the top, that looks like this. Actually, that's a very clever one, and I know who did that. That is your world of projections. People tend to take the 3D world and try to find different ways of projecting them in 2D plane. But this 2D projection causes issues. Okay. Now you can see that this particular sort of shape, it creates a tear. Okay. Now this would have been joined together in real world. But now if there was a country in there, now because of that 2D projection, it's split apart. So that means the distances, if we measure the distance between the two locations, they're going to be incorrect. So projection has just suddenly introduced errors into our data. So you take the 3D world, we thought, okay, we'll make it simple in 2D, but as soon as we made it 2D, we introduce errors. And this is what the world will look like if we had projected it from that 3D globe into a 2D flat, relatively flat surface. But peeling an orange is good enough, but we still need a much more systematic and mathematical way of projecting. So there are three basic approaches that are used to take a 3D world and project it into 2D planes. So if you imagine the round spheres in here, are those ellipsoids or the world itself? So the first one on the left here is a cylindrical projection. So what you do is you take the globe, you fit it inside a cylinder of paper, and you imagine that there's a light source inside the globe. You turn the light on, and whatever the surface features are, the boundaries, they will project on the inside of that cylinder. So you take a piece of paper, basically. You rotate it around, you take an orange, you put it inside, you turn the light bulb on. The boundaries that are on the surface of the globe will project on the inside of the piece of paper. Then you take the cylinder and then you open it up, and voila, you have your projected surface. That's easy enough, right? Or you can create a cone, okay? And you can put, again, the globe inside it, project it on the inside of the cone. Or you can take a planar surface. So you just take a piece of paper and project it just onto that surface. So there's three common ways of projecting. But it's done so delicately that there's only certain parts of the paper that touches the globe. You can't wrap it because the paper can't be wrapped around. So only that certain part touches the globe. And during that projection, the part that touches the globe is the only part that is perfectly accurate on the 2D plane. The further away you go from that touching point, you start to introduce inaccuracies. So I said three different types. But if you take each type, let's say in this case, cylindrical projection, there are two deviations. So one is what we call a tangent projection. So you could have a cylindrical tangent projection. The other one is called a secant. So a cylindrical secant projection. And the one that earlier on that I showed you, where the globe fits perfectly inside a cylinder, touching just that one little equator in this case, is called a tangent. But then we can also simulate a smaller cylinder cutting through the globe, so it actually touches on two parts of the globe. What does that mean? It means that those two areas that are touching the cylinder will be the most accurate. But then you're going to start introducing a lot more exaggerated errors where it's not touching. So you can make this something big, we can make this something small. So we had three different type of projections: cylindrical, conical, azimuth, or planar. Now we have two for each type, so we can have cylindrical tangent, cylindrical secant, conical tangent, conical secant, planar tangent, planar secant. Okay? Stay with me, there's more. Haha. So now what we can also do is, let me just move myself around. That we can take each of those cylinders, and we can keep them straight, which is a normal projection. So the equator is touching the inside of the cylinder. Or we can turn the cylinder 90 degrees so the poles are touching the inside of the cylinder and on some sort of meridian. Or we can take a cylinder and then adjust it obliquely in any direction so another part of the globe is touching the inside of the cylinder. Again, why would we rotate? Because we know that the one projection will not be able to accurately map the whole world, and we know that the most accurate measurement will be around that sort of a circumference which touches the inside of the cylinder. So we rotate the cylinder around to whichever part of the world we want to map, right? So cylindrical projection, conical projection, planar projection. Each cylindrical could be tangent or secant, so secant will be cutting through. But each of them could be normal, transverse, or oblique. So suddenly, we have, just on the types of projection, they were generic. We can have cylindrical, normal, tangent, that's one. Cylindrical, normal, secant, that's two. Cylindrical, normal, cylindrical transverse. I've even lost count. So there are about 18 odd different types, right? So this is just the basic and fundamentals of how we project our 3D world into a 2D plane. How many projections, you ask, that can be in the world? Well, countless. Seriously, there are so many. I think there was this number that there were about 5,836 or something projections. But pretty much we can keep on creating these new projections depending on which area we want to map and how much accuracy we want. If we want it global and so on and so forth. If it's for visualization, if it's for a particular other application, if it's for navigation. Because what happens is that these projections will cause errors. And let me see if I could show you an example of it. Now, this is something I created earlier with some locations identified in the world. Okay, and this particular projection is the Google's projection of Red Mercator. And we will talk about a bit more in detail about these in the upcoming episodes. But I created a 500-kilometer buffer around every location that I randomly chose. Now, watch what happens when I change the projection. So I am going to go to a WGS84. What in the world? Look what's happened to those circles. They're still 500 kilometers apart, but completely destroyed the shape. So you can start to see that around the equator, it was fine. Probably still is. But as further away you go, your shape starts to distort. Okay, let me choose a local projection for, let's say, British National Grid. Oh, wow. You can visually see the problem that's appearing in here. Now, interesting thing is that the two dots that you actually, two locations that you see here, in the UK. One is in London and one is somewhere in Scotland. And both of them, the circles, they should be the same. There it is. They should be the same, but they don't look the same. So even British National Grid, going all the way from the south of UK to the north of UK, could actually cause a lot of problems. Okay, let me give you another example of exactly how much distortion these projected maps can create. So this is a projection that we're quite used to. It's called Mercator projection. It's a cylindrical projection. So you see the size of Greenland, which looks pretty much the same size of Africa. Okay, to actually move that across, this is a great website. You guys should try to go through it. It's called the truesize.com. So when you actually see the Greenland size and try to bring it to Africa, you actually start to see exactly what the relative size is. It's not as big. Okay. Anyway, coming back to this, I like projections. Some of them are really pretty. And some of the Sensat people will actually know this particular projection as well. Okay. I like projections. They create pretty visualizations and sort of clever ways of taking that to a 3D environment and trying to keep as much integrity intact. I like them. Some of them are very pretty as well. But then the cleverness comes in, really, that when you really take care in taking that peel of that orange, the surface of the earth, and then try to peel it in a way that a particular feature, no matter how long that is, its accuracy stays intact. Okay, so imagine peeling it in a very sort of spiral sort of form. The world will look like that. Okay, or a map of that projection will look like that. Well, I think that's quite beautiful as well. Now, the interesting thing is that if you actually do a projection, something like this, pretty much around the center of this data, most of the areas will stay intact. So it's really good for linear mapping, right? Ladies and gentlemen, I give you the snake grid. That's the idea behind the snake grid, okay? But you also know that the linear area that's been mapped is going to be quite accurate on a very long distance. But at the same time, other parts, the further away you go from that linear spine, it's going to be completely destroyed. Okay? Well, I'll leave you with an example of the distortions that a Mercator projection that we're pretty used to. All the big, large printed maps are based on Mercator. Google's based on Mercator. All the online services are based on Mercator. So I'll give you at the end an indication that how the shape and the size of the countries are distorted if you choose the wrong projection. So what you see on maps is not what you always get. Okay? And that's it for this one. I hope you understand a little bit more about projections in general. Next week, we will talk about coordinate referencing systems. I think that's a much complicated sort of form. The idea would really be that I take this projection, take this projected map, and try to put a grid on top of it so we can start to measure distances or any other type of mapping exercise. Okay, well, that's it from me for now. And I'll see you probably in a week's time for another lecture.
Hey, well, welcome to this new series of Sensat College. So the idea